the cloud. All right, well, we are continuing with the second lecture by Pierre Toledano.
Thank you. All right, so I want to apply all what we said to an example, which is a textbook example of structural transition, which is barium titanate. So barium titanate is known because we have 3 successive transition at nice temperatures, 125, -90, and they have been investigated by many people and experimentally, theoretically. All right. So we have a sequence of ferroelectric P4MM, AMM2, P4MM, it's the same than PZ. We have something along one of the, since we start from a cubic phase, so it's along one of the fourfold axes of the cube. AMM2, it's in a plane. It's orthorhombic in a plane with a twofold rotation, and R3M, it's rhombohedral. It's all right. It's also, let's say, with the polarization along the diagonal joining 2 corners of the cube. And all the transition, the first one is very slightly first order, but it is first order because there is something which clearly shows it, which is a double hysteresis loop, which can occur only when you have either antiferroelectricity, which is not the case here, and or when you have a first order phase transition. So you have 3 first order transition. Just I have drawn here the, let's say, this is P4MM, this is AMM2, and this is, so we have to use all what we know now to see what is the phase diagram, how many domains, and all that. So P4MM, we have 6 ferroelectric domains, plus or minus, plus or minus, plus or minus, 3 ferroelastic domain, because you have a strain which couple to Px, Py, and Pz. I have drawn here the form of the strain tensor. So you have coupling of this type. Then you have 12 ferroelectric domain for the second, because you have 4 point symmetry element, 48 here, 48 divided by 4, it means 12. So you have 12 ferroelectric domain.
Yeah, I'm sorry. I'm sorry. I'm a bit lost. So before you discussed just the coupling PZ squared EZZ. Now you take out of the head this different coupling to a particular component of 2 EZZ. So where does this come from? Why this particular combination?
Because if you calculate, this comes from another irreducible 3-dimensional. In the cubic phase, you have 2 3-dimensional irreducible representation. One which span a vector, the polarization, and one which spans the ferroelastic strain, the component of the ferroelastic strain. They couple. You have 2 3-dimensional irreducible representation, and you have to calculate the coupling between them. It's a complicated story because you have 48 matrices, but finally you get this. All right?
Okay.
And, all right. And here it is a bit more complicated because you see that Px, I don't understand your question because it's exactly as in the other time, but of course the form of the strain depends on what is deformed. You see here you deform a cube, you don't deform, let's say, tetragonal along one direction, you deform everything in the cube. It's a real deformation. It has been measured. And here, So this is not a, let's say, working example. It's a real one. And here you have 12 ferroelectric domain, and the coupling takes this form, px, py, exy, and you have also something related to that. Because, and finally, R3M, you have the three components of the polarization which are equal. You have 8 ferroelectric domain because R3M has 6 symmetry operations, the point group 3M. And so 48 divided by 6 gives you 8. And so you have 8 ferroelectric domain. You have only to change the sign, minus P, 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 P minus P, P, and so on. And so 4 ferroelastic domain, always half of the ferroelastic domain with respect to the ferroelectric domain. So it's a proper ferroelectric. The primary order parameter is really, and this is a textbook example of proper ferroelectric, where the primary order parameter is the polarization, and it's an improper ferroelastic because E is a secondary with respect to P. Okay. Now it doesn't work, this. Sorry, perhaps I don't press as I need. Okay, thank you. So here I have written not the 48 matrices, which is possible, you can find it in many books, but the six matrices generating the 48 matrices, because it is sufficient, if you want not to calculate too much, for calculating the basis of integrity. And you find that the basis of integrity, you have, of course, the standard square, 4th degree, the sum of the 4th, and you have a 6th degree term, a 6th degree invariant of the polarization. So if we follow what we said, the dimension of the order parameter is 3. The dimension of the integrity basis is 3. So we have 2 power 3, 8 possible stable states, not only 3, the one which are well known. And I want to say that so here are the 8. You see they correspond to this equilibrium value of px, py, and pz. The 3 which have been observed during long time, they are here in the first row. And the other one, they are not some illusion or some prediction that will never be realized, because one of them, at least, have been observed under applied field. I don't know which one it is, CM, PM. I think they did not go to the end of the story. But when the Landau theory predicts a number of phases, they all exist, but to put them in evidence, there is no rule saying that only the higher symmetry will be observed. This is wrong. Now, here I have drawn 2 possible representation diagram in the integrity base. So you see that phase 1 is the cubic phase. Then you go to phase 2, which is the P4 MMM, the ferroelectric phase. The 3 ferroelectric phases which are here are the curves which start from 1. It's a 3-dimensional space. So 1, 2, 3, and 4 down. The surfaces between the curve, you have 3 surfaces, is the second row here, CM, PM, CM. And the volume inside the surfaces is P1, has the symmetry P1. This is a cut in the I2, I3 plane where you can find this phase. So this gives you an idea of what can be the topology of the phase diagram. We see that in order to have 8, we need to have 5 and 6, because it will be always 5 and 7. It will be always between them, or 5 and 6. For example, phase 4 will be always between phase 2 and phase 3. Let's check that, because many calculations have been made for the phase diagram. Here I have drawn the phase diagram.
But Pierre, I mean, I'm a bit confused. Are you so this diagram of various phase relations? Was it based on what? On group subgroup relations, or on the fact that p's were varying continuously? When you say that two phases are nearby, is it under assumption?
Sorry.
This diagram on the right for different phases. When two phases are contained by a line, what is the mathematical rule which tells you what the two phases are?
For example, this one is the intersection between these two.
I don't see your pointer, by the way.
You don't. Sorry. Here.
The pointer is not transmitted to people who are online.
But so please, what do you want exactly to know?
Well, for example, let's look at phase 1, and it's connected by a line to phase 4.
Yes.
What is the mathematical rule which tells you that these two phases are connected? What is the like? Does it mean that one group is a subgroup of the other group, or something else?
No. There is a way to determine all the stable state, let's say visually. Of course, after that, you need to show that the phase which you have found correspond to an absolute minimum of the free energy for a certain rank of the coefficient, and that it is not unstable. It has to be stable, of course. So you have, of course, to minimize the thermodynamic potential by classical methods, the minimization first derivative, then second derivative for the stability. But the symmetry, AM, to all the symmetry, that this you can determine them visually, because you have to take, for example, AMM2. Let's take AMM2 since it is the case that you want. You see that AMM2 corresponds to Px equal Px. So the two first components are equal and the third is 0. So you look on the 48 matrices of PM3 bar M, which matrices keep invariant the two first place. You see, for example, you have 3 by 3 matrices, and you need to find the subgroup of matrices among the 48 ones which leave invariant the two first Px, Px. So you need to have, for example, they can be, of course, exchanged between them, but they cannot, the third term, the third quantity must not leave them. Okay, I have to show here, yes. For example, you see here.
When you say here, I don't know what you're talking about because I don't see the pointer.
Sorry, the C3 2x, the second matrix on the first row. That Px transform in Py, Py transform in Pz, and in Px. So you have an exchange between the three components. But if now you take u x bar y, or I, u x bar y exchange 1 in 3, 1 in 2, and 2 in 1. This would fit for Px, because 1 is transformed in -2, and 2 is transformed in -1. So this, you know that u x bar y can give you, correspond to this stable state. There is a visual, but I need, usually what I do to teach that, how to determine all the stable states from the matrices.
I mean, I understand how to determine stable state. I don't understand why certain stable states are connected to each other by a line and others not. What is the rule which says that two states are connected? For example, AMM2 is connected to CM. Why are they connected? What is the rule?
Okay. So you speak about not only the second line, but the third one.
Yeah, for example, what does this mean?
Because if you take the intersection of P4MM and AMM2, it will give you a phase of symmetry Cn. It can be, of course, phase 7, but then you have to look carefully on the structure, and then you understand that phase 6 keeps some memory of P4MM and AMM2. It's not simple, but you need to go to the structure, of course, not only on the pure symmetry. But pure symmetry gives you a lot.
So that's more than just symmetry. That follows also from the Landau Hamiltonian. You have to think about in terms of Landau Hamiltonian in order to get these relations.
Yes, but
I see.
Yes.
Okay. Okay, thank you.
Oh, please. So let's go to the next. So I have drawn, there was a student in Rostov on the Don who made his PhD on barium titanate, and he drew all phase diagram up to the 12th degree. It's beautiful. I took some of his phase diagram. This is to the 6th degree. You see, at the 6th degree, you have phase 2 and 3. Phase 2 and 3. So I wrote R3M and P4 on MMM, which are not groups of group related. So it's necessary first order between them. If you go now, this is for D1, the coefficient D1, which is the coefficient of I3, which is negative. But when the coefficient becomes positive, then you have a phase which appears, which is precisely phase 4. Phase 4 appears because phase 4 is the intersection of phase 2 and phase 3. And so it appears between phase 2 and phase 3. But there is an inconsistency, which I have noted, is the fact that the first order transition line coincides. Okay, I will use this for the people here. It coincides with the limit of stability. This is not possible. So then you have to go to the 8th degree, and then you see that phase, it appears phase 5 of D1, but phase 4 is here, you see, and phase 6. And so you can go, you need to go to 12 because you have a 6th degree only for first order, for second order transition. And you need to go to the degree 14 if you want to have really the full phase diagram with first order transition and so on. And you must be convinced, because this is not the only example. We have other examples where these low symmetry phase, they can appear. They can appear at high pressure or in other conditions if they don't appear with temperature. All right, so this is all what I wanted to say about barium titanate. And now we can go to some other ideas. Let's say I want to introduce the concept of image of a group, because the image of a group allows to determine all the free energies associated with an order parameter. Let me start again with barium titanate. Barium titanate, as I said before, have 48 matrices generated by these 6. All the 48 matrices of barium titanate are different, all 48. So there is a one-to-one correspondence, isomorphy, between the 48 matrices of the irreducible representation, the 48 matrices of barium titanate, of M3 bar M or PM3 bar M, which is the same, and the 48 symmetry operation. One can say that this irreducible representation, 3 dimensions, of PM3 bar M is a faithful irreducible representation of G0. By contrast, the 2 irreducible representations that we have considered before of 4 on MMM, the one-dimensional the one-dimensional representation, gamma 1, let's call it now, spanning Pz, and gamma 2 spanning Px and Py, they are not faithful because you see you have +1, -1, and so you don't have all 16 numbers. You cannot have, it's one-dimensional. You have either +1 or -1. So it is not a faithful irreducible representation of the 4 on MMM group. The same for the gamma 2 representation, because you have 8 matrices which are different, and the other 8 are exactly the same as the first 8, and so they are not faithful. You have a homomorphism between the 16 matrices and the elements of 4 on MMM. Now, here I can introduce the concept of an image of J0. It's the set I0, let's call it, of distinct matrices of an irreducible representation of a group G0. And so the image forms a group I0, which is homomorphous to a subgroup of G0, which can be G0 itself. So the image group gamma of M3 bar n is isomorphous to M3 bar n. The image group of gamma 1 is isomorphous. You see, we have only 2 numbers, 1 and -1. It's isomorphous to a subgroup composed by 2 elements of 4 on MMM, which can be 1 bar, C1 and inversion. It can be 2, C1 and twofold rotation. So the image group is isomorphous to either to any of these 2-dimensional subgroups of I4 on MMM. And the same, the 8 matrices, the image group gamma 2 of 4 on MMM I0, which is composed by 8 matrices, is isomorphous either to 4MM or to 4 bar to M or to 4 to 2 or to 4 on M. You have many subgroups composed by 8 different matrices. Now, let's go a bit further. The n-dimensional irreducible representation of G0 carried by the n-component order parameter. The image group I0 of gamma, it's isomorphous to an irreducible subgroup of the orthogonal group ON. Why? Because first, all the matrices, they are real, they are unitary, and so they are orthogonal. So they are necessarily subgroup of the orthogonal group. And so if we can calculate the subgroup of the orthogonal group ON, we can calculate, we can determine all the possible free energies with index n, n is the dimension of the order parameter, associated with the n-component order parameter. So what do we have to do for that? We have first to enumerate the irreducible subgroups of ON. And secondly, we have for each subgroup to work out all the invariants of various degree, which are consistent with the order parameter. All right, the next slide will show that. Let us enumerate all the irreducible subgroups of ON and free energies associated to these subgroups. Let's start by, let me only say that this has been fully done for n smaller than 4, smaller or equal to 4, and it has been only partially done for n equals 6, 8, or 12. So there is something that you can do, is to do it for 6. The work is not finished. The subgroups of O6, O8, O12, and so on.
But is it phenomenologically motivated? Are there interesting materials where the order parameter has dimension 6, 8, 12, or whatever?
For 6, yes. For 8 and 12, you can find them in magnetic phase transition, not in structural. But all structural phase transition have not been already discovered, so you don't know what will happen. But at present, and I will show this tomorrow, you have many examples of 4 and 6. 8, I could not find material. But we have, of course, irreducible representation. You see, we have irreducible representation inducing structural phase transition, which have 8 dimension, 12 dimension. You can go up to 48 dimension, which is the maximum dimension. But of course, to find a concrete example, it's another story. So let's take the O1, because each size of n, each number of give interesting an interesting, let's say, physical situation. Let's take first what are the subgroups of O1? We have 2 subgroups. We have 2 subgroups. We have one, the subgroups composed by the identity, and so we have a single basis of integrity, which is I equal eta. Let's call, from now, I will, let's say, generalize my notation and use the letter eta to, let's say, denominate the order parameter. So let's take, we have the basis of integrity is eta. So we have all the powers of eta, eta 2, eta square, eta third, eta fourth. And this is interesting because you see it's, for example, the transition between liquid and gas. The transition between liquid and gas is described by this type of free energy where all the power of the order parameter are there. But of course, it has been shown that you can get rid of the linear term in the free energy, and so you come back to this free energy which I had shown before with a second degree, third degree. You cannot get rid of the third degree term, so you have second, third, and fourth. And so you can describe the liquid to gas phase transition. Here I have told you have, let's say, sorry, I use this. You have to get rid of the linear term, you have to put, to introduce that it's not, you have eta minus eta 0 and eta 0 on the other side. And of course, we all know that the liquid gas transition ends at a critical point. And so around which you can turn continuously, let's say, because you cannot recognize if it's a liquid or gas. And I want just to mention, because I have only very recently worked on that, you have exactly this situation in magnetic system, where the spins go from one direction to the other around the critical point, the critical end point. Now, second situation, and you have also the Landau point in this case. Second situation, eta square. This is another subgroup of O1, which is composed by where the image group is composed by 1 and -1. We have already studied this example, and this is the, well, we have already studied this case where you have the 2 phases, the origin, and 1 phase which is stable below TC. Now let's move to O2. Here I have used, I'm sorry, another notation for the point groups. This is known as the Sunfish notation, which is much more, let's say, synthetics. So we have 2 subgroups, 2 classes of subgroups for O2. They can be denoted CNV and CN. CN, it's very simple. It's the cyclic group. You take an axis and you multiply it by itself. So if you take 4, you have 2. You have you see, if you multiply, it's called cyclic group because it's only composed by axes along one direction: C3, C4, C6, C8, C12. And C and V, well, I can note it in a different way. 4, it's simply 4 mm. 6, it's 6 mm. 8, it's C4V is 4 mm. C6V, 6 mm. So just to help you putting a bridge, because between the Sunfish and the Hermann-Mogan notation. What is interesting in this notation, which is a notation, then you can write eta1 and eta2 in polar coordinate. So the two invariants, you have one invariant which is rho square, and the other invariant which is rho n cosinus n theta. And so you know that all your phase diagram will have this shape. We have already seen this, but this works for 4 mm, for 6 mm, for 8 mm. You always have 4 phases. All right, 1, 2, 3, 4. Now, so 4 stable phase, and we have to go to the degree 2n to have the full phase diagram. And now there is a particular case which is n equals 3. N equals 3 because you have a cubic term. You see rho 3 cosinus 3 theta. And so you have only first order transition. In reality, the phase diagram is very interesting because you have 1, 2, 3, 4, but 2 and 3, they are anti-isostructure, which means that they are the order parameter, the same structure, but the order parameter has opposed sign. So this is.
So can I ask a question, Pierre?
Yes.
So when you list these Schoenflies groups, I think so you're using some additional information that other subgroups of O2 do not appear under this image procedure that you described. So you're only listing, you don't list all subgroups of O2, you only list those ones which can appear as images of point groups.
But what other subgroup do you want?
Well, like for example, C5 is not in the list because it cannot appear as an image.
No, but C5 you don't have 5-fold rotation.
Exactly. So that's what I was wondering. Yeah. So there is some extra information that
yes, you need to be consistent with, let's say, crystallography.
Okay.
All right. No, it's the full set. You don't have others.
But to do this, you have to use point groups or also space groups to do this classification that you're doing now.
Here it is the image group. The image group, it's a different group. It's not a point group. It's not a space group. It's a separate group.
Yeah, but on the previous page, you had this group G0. Was G0 a point group, space group? What was G0?
What is the
on the previous page there was G0. You said it was image of G0, but you never said what G0 was.
Okay, let me go back.
Image of G0.
This I0. Is this what you are meaning?
So here you say image of G0. What's G0?
Where is G0? Yes. Well, no, G0 is a group.
Which group? Is it the space group of the crystal?
Okay. Yes. No, not a space group. Yes. Wait. Okay. You let me take my time to answer you. It's form a group isomorphous to a subgroup of J0. No, it's a set of matrices. So it's a point group. J0 is a point group. Okay, not a space group. Because space group has an infinite number because of the translations.
Okay.
So it's a point group.
Okay, thank you.
All right, please. So CN, the cyclic group, so-called. You have an additional invariant which appears, I3, which is rho n sinus n theta. But you must be aware that if you add I2 square and plus I3 square, you will find I1 power n. So they are not completely independent. But the phase diagram is this one. It's a sort of cone type which unframe the I1 axis. And so you have only two phases, because more you add invariant, less phases you can stabilize. So here you will have only two phases, 1 and 2, two is in the volume inside the cone, and one is at the origin of the cone. And again, a special case is C3, because C3, because of the third degree term, has this shape. It has two possibilities of phase diagram, the one here and the one there. The one here ends at a critical endpoint with two isostructural phase, and here it terminates on the line which separate 1 and 2. Okay, so this is, now let's go to 3. So O3, three-dimensional order parameter. We have 5 irreducible subgroups with image I0, which are isomorphous to the 5 cubic point groups. We have 5 cubic point groups, which are denoted T, TH, TD. I took the two notation here. T, it's 2, 3. OH is M3 bar M, and so on. And so this has been done sometimes before. And so you see that you can immediately, if you start from T, which has the maximum number of invariants, you see that they have a 6 degree invariant. So you have to go to the degree 12 and you find 5 stable states in the free, as minimizing the free energy. Here you have to go again to 12 and you have again 5 stable states. For TD 4 bar 3M, you have 3 invariant. You have to go to the 8th degree and you have 8 stable states as for M3 bar M. And here you have again 5 stable states. Now, this is a result which have been obtained by Louis Michel, my brother, myself, and Edouard Brezin in 1985. It's we have 27 irreducible subgroups and 3 energy of O4. They are all listed, but only 22 of them might correspond to a second order transition because the 5 other have a cubic term. Now, for O6, we have the result for structural phase transition, but it's not the full list of subgroups. So we know that we have 32 image and 3 energy, but it's only for structural transition. We might have more for magnetic transition, and so this work has not been done, has remained to be done. All right, that's all for this. Now I wanted to, in a very short way, because it's something which, you see, people in material science, I belong to this community of material science, they like to use and to Landau theory, but what stops them every time, it's the construction of the irreducible representation. This I tell them that they would need 1 month to work hard to learn it, but 1 month is too much apparently for people for material science, but I am sure that here you have the time. You need to not only to know how to construct the irreducible representation, but you need to construct some of them. And so after 4 or 5, then you know you have you can construct any. So here I will only give the method. So let me remind you that structural transition between crystalline structure correspond to transition between the 230 crystallographic space group. A space group is a group of infinite order, which is formed, which contains symmetry operation of the type RT, where R is the point symmetry operation, rotation, reflection, inversion, and T is translation. And so the set of R form the point group of the crystal. It's a finite group, and the infinite subgroup of T generating the 3-dimensional Bravais lattice. So great T is a subgroup of the set of translation, because you don't have only lattice translation, but you have also you have, let's say, fractional translation, which occur, for example, when you have a helicoidal axe or glide plane. So the irreducible representation of the 32-point group have been tabulated. Because it's a finite, they are finite. The irreducible representation of the infinite space group is infinite. And so they have not been tabulated, but they can be constructed starting from the irreducible representation of the point group. How do you construct that? Well, let's say that irreducible representation requires two indices, K and M. K is a K vector, is a wave vector, let's say, of the reciprocal space, which belong to the first Brillouin zone of G. G is the parent space group. And so K defines a subgroup, J with index K of J, which is the set of operation, space operation RT, whose rotational part L leaves K invariant or transform it in an equivalent vector differing by the reciprocal lattice vectors. So G index K has irreducible representation to n of K of dimension n and index m, which are tabulated, and they have been tabulated by Kovalev. Kovalev, the book of irreducible representation of the JK opened a new era for people working on phase transition. It was in 1961. And when the table, because before people had to construct, and so it was a bit discouraging, but using the table by Kovalev, everything became very clear. And so then how do you construct from the gamma K, so the irreducible, the final one, constructed using tau m of K, which is tabulated by Kovalev? First, you must know that gamma has the dimension n multiplied by r, where r is the number of vector of what is called a star of K, which is the set of reciprocal vector of the first Brillouin zone, an equivalent to K obtained by applying all point symmetry elements R. So once you know that, then you have to take an example and to try to construct the irreducible representation. Just to tell you that it's not something impossible, I have constructed for my PhD around 3,000 irreducible representations using, of course, Kovalev table. It was before things had been. Now there is a condition that has been proposed by Lifshitz, which reduces the number of irreducible representation. In reality, it's a false reduction because, of course, I will explain. It's only if you want to have a transition between strictly periodic structure. But people discover after some time that sometimes the low symmetry structure is not strictly periodic. It's incommensurate. So this Lifshitz condition, if you impose it, it will limit to a finite number, about some thousands, the number of irreducible representation of the space group. But if you don't accept the Lifshitz condition, and this will allow you to describe the many incommensurate structures that have been evidenced in the solid state. So let's speak about the Lifshitz condition that was very useful. So K is a vector which varies continuously in the first Brillouin zone. And so the number of irreducible representation, gamma Km, is infinite. Lifshitz in 1941, in a well-known paper, understood one point, which is that the absolute minima of f as a function of the order parameter is insufficient to test the stability of strictly periodic phase. We wanted to have a transition between really two structures strictly periodic. And f has to be not only minimum if you want to have strictly periodic structure, with respect, it has also to be minimum with respect to small variation of the order parameter. Small means, for example, proportional to the first derivative. But the first derivative, let's say d eta on dx, is not invariant by the high symmetry group because it is proportional to the order to eta, and we know that we don't have any linear term, so we don't have first derivative by themselves. What we have, it is product of the order parameter multiplied by one of the derivatives. This we have because it is proportional to eta square, and eta square is invariant by the high symmetry, by the symmetry operation of the parent state. Now, the Lifshitz invariant is an anti-symmetric combination of eta, the order parameter component, and the derivative of the order parameter component. Why anti-symmetric? Well, simply because symmetric like this will not affect the stability because it's simply the derivative with respect to eta y, eta j, and this when you sum, because of course then the free energy become to be not only polynomial if you take into account the derivative, it becomes to be integral over the volume of the system of a free energy density. And this free energy density contains the Lifshitz invariant, which is an anti-symmetric invariant of the order parameter, and the so-called Ginzburg term, which is the square of the first derivative, which is required if you want to stabilize. Let's say when you minimize the free energy using Euler-Lagrange equations. Now, the Lifshitz condition is this one. No anti-symmetric invariant of this type should be permitted for transition between strictly periodic phase. So, and this condition limits to a finite number the number of irreducible representation between strictly periodic structure. J index chi has to, because J index chi has to contain either inversion or three intersecting twofold axes to have this type to forbid Lifshitz invariant. And this is realized only at the center of the Brillouin zone and for a few high symmetry points, as they are called, of the first Brillouin zone surfaces. So we start from an infinite number of irreducible representation, but the Lifshitz condition reduces this number to a finite number. So it becomes finite, so it's a work which can be done, and it has been done in the beginning of the 80s, and then Stokes and Hatch, American, they used computer, and you have a very nice book where all the irreducible representation of the space group are given with all the symmetry, low temperature symmetry phases, which can be deduced from the free energy. Now, I think it's to conclude. Yes, it's to conclude. I want to speak of something which is important in the field of structural phase transition, which is phase transition induced by several order parameters. Let me come back on the example we gave at the first beginning of the first lecture. We said that we cannot have the two coefficients, A2 and B2, which vanish together, which change sign together. This is why only a single irreducible representation can induce a phase transition, a second order phase transition. Now we have two cases which have to be considered. First case, if the two order parameters, here it was for A2 it was Pz, and for B2 it was Px Py. The coupling between them is Pz squared multiplied by Px squared Py plus Py squared. Why is it so? Well, because they correspond to different irreducible representation. And as soon as you have different irreducible representation, you have a biquadratic coupling term. So here we have a biquadratic coupling term. And what's happened with this biquadratic? Well, this problem was in reality studied by Leafy himself in 1943 in a nice paper. And what he showed is that you will have two successive second order phase transitions. The first phase transition. So you have A2 and B2, which change sign consecutively, one at TC1, the second at TC2. So below TC1, we know that, let us assume again that A2 vanish first, change sign first. So we will have Pz and the symmetry for Mn. Then you cool, and then the second B2 come cross TC, change sign, and so you will have a phase in which you will have the three components, two components coming from B2 and one component coming from the vanishing of A2. But of course, you will not have the symmetry given by B2. You will have only one, because one is the intersection of 4 mm with the different symmetries related to Px and Py. And so you will have a symmetry 1, and here is the phase diagram I have represented here. So you have 4 mm, it goes to 4 on MMM, it goes to 4 mm, and then it goes to 1. The group 2 mm, which should be induced by Px, Py, will not appear in the phase diagram. And we have another case now. If we have a strong coupling, strong means that, for example, delta is large, or that the two curves are very close to one another, we have what is called a triggering mechanism. One order parameter will trigger the other one, and in a very small interval of temperature. And so what will happen is that you will not have one second order transition as here, followed by another one. You will have a single first order transition to the phase 1, because there is a jump that will appear. And there are many examples in structural phase transition in this case. For example, here, PbZr03, it's a well-known material for different reasons. And you see, you can decompose. It should go to IMMA to P2, but in reality, it goes directly to PBAM without passing by this. You have a strong coupling between these two, let's say, irreducible representation.
But sorry, I'm confused by this example, Pierre. I trust, of course, that this is observed, but how is this happen? Even if this coupling between Pz squared and Px squared plus Py squared is large, close to the first phase transition, the value of the order parameter is very small. So no matter how this coupling is large, if you go very close to the first phase transition, it can be neglected. So how can this intermediate phase completely disappear? What is the physics?
The physics is that you see the triggering mechanism can be in both sense. Either the one which is close to second order, let's say, triggers the other one, or the other one triggers. In reality, what will happen is that the transition appear to be squeezed in a small region. It is squeezed. You see, you don't have separation between the two. What people try to do is, for example, to apply a field to see if you cannot separate the two, but in reality they are squeezed, they are close one from another. They were already very close above TC, and so it gives only one phase with one symmetry, which is the intersection of the symmetries given by the two. I understand your argument, but it's like that. I mean, it appears as squeezed, and you have many examples. I mean,
no, but I'm sorry, but before you are telling us for a long time that we should trust this Landau and so on. So can you demonstrate by the computation from the Landau Hamiltonian that this phase just disappears intermediate, or will it always be present but very narrow?
It's not me who demonstrate that. It has been already demonstrated. It's a paper by a man, his name is Holakovsky. He introduced this concept of, let's say, triggering mechanism.
But I don't understand how mathematically it can happen. And can you explain, if you're close to the first transition, this term can be neglected. So where am I wrong?
Don't forget that you need to, the basis of integrity, when you have coupling, the coupling term pertain to the basis of integrity. You don't have the same phase diagram that when you separate the two, you have a supplementary term in the free energy. And depending on the sign of the coefficient and all that, this additional coupling term may, let's say, destroy the possible stability of the phase that would have occurred across a second order transition.
Okay, just to summarize, you claim there is a Landau Hamiltonian which shows this behavior.
Yes.
Okay.
Yes.
Slava, is it possible that the difference is that the minimum is not at close to p equals 0 anymore?
Sorry, can you ask again your question? I shall repeat it.
So in the case you're talking about, it's a first order transition where you develop both order parameters at the same time. Is that what happens?
Well, it's not exactly at the same time. It's, well, because at the same time we said at the beginning that this was not possible. It's one which triggers which brings to 0 the other one, but it's a consecutive mechanism. Yeah, because if it was at the same time, it would be unobservable. Or here you observe the phase which appears, and it's not this mechanism of triggering is different than the simultaneity of vanishing at TC of two modes, of two, let's say, coefficients. It's a different mechanism. Landau was perfectly right when he said that you cannot have because it would not be observable. But here it is observable only because you have a jump that will happen. Instead of having something smooth, continuous, you will have a jump in both. Let's say it will give you some mixed situation where you will jump over, let's say, some region. And these transitions are always first order.
So you have a crossing between, in free energy, between the minimum at px and pz is 0 to a new minimum which has non-zero px and pz.
Yes.
Yes. Okay. Thanks.
All right. I just want to finish this second lecture by saying that biquadratic coupling is not the only coupling which have attracted interest, and we have also linear quadratic coupling. We have two types of linear quadratic coupling again. You have what we have already seen at the beginning, the primary order parameter, which couple to the secondary, and you have effectively a coupling between eta square, which is the primary order parameter, and psi, or I don't know the name of this Greek letter, zeta or psi, which it would be the strain. This is called improper coupling. We have already spoken about that. But you have another case. You have case 2, which is an interesting case, where eta and zeta have different symmetries. And despite the fact that they have a different symmetry, they have a coupling which is linear in one of the order parameter and quadratic in the other one. By the way, you know that I only consider the lowest degree coupling. It's the only one which is important. Higher degree coupling can give you something far from the transition, but for understanding the transition mechanism, you have to take only into account the lowest degree coupling. So here you see what will happen. It's very interesting case where you have one order parameter, eta square, eta 4, psi square, psi 4, and linear quadratic coupling. It will give you this phase diagram. The parent phase, psi equals 0, zeta, eta equals 0, but then you will go directly to a phase with eta different from 0, psi different from 0. You will not have the phase with eta equal, and you will have also a phase with eta equals 0, zeta, or psi, I'm sorry, different from 0, but you will not have the phase with eta different from 0. So you have the disappearance of one of the possible phase because of this linear quadratic coupling. So psi destabilizes the phase with eta different from 0, psi equals 0. The last type of coupling, which is of interest, is the bilinear coupling, eta psi. And this happens when the two eta and psi have the same symmetry. This, for example, there is a textbook example, which is, by the way, material having a second order transition, KDP, potassium dihydrogen, and so on. And so here, PZ has exactly the same symmetry as EXY. They transform both by the same one-dimensional irreducible representation. And so you have a bilinear coupling. The problem was, what is the order parameter? Is it PZ or is it XY? Well, there was a very nice experiment to determine which one of the two was the order parameter. They clamped the crystal to forbid the deformation to take place. And then the transition occurred. So it means that the strain was not the primary order parameter, it was the polarization. And so, okay, this is the conclusion. But the phase diagram is also very interesting because you see, you go from eta equals 0, zeta, you go to a phase where both order parameters are non-zero. But then you have below region where you end again at a critical endpoint between two isostructural phases, both of them being with eta different from 0, zeta psi different from 0. All right, I will stop because tomorrow I will only discuss about the critical behavior on, I will come back on all these results only from the point of view of the critical behavior with a list of material. It will be much more concrete lecture tomorrow. Thank you.
Thanks, Pierre. Are there any questions?
Yes.
Can you repeat also the question, Pierre, when you hear it?
Yes,
when...
yes, I shall repeat. In KDP. In KDP, it was.
What was the question?
Sorry, I was asked what was the critical exponent in the case where the two order parameter coupled by linearly have this same symmetry. Well, as far as I remember for KDP, but I'm not a specialist of KDP, I think that it's one of the cases where you have a logarithmic correction to the classical exponent. I will check this evening to say, let's say tomorrow. You have some, let's say, because it's a uniaxial ferroelectric. And uniaxial ferroelectric, we have a lot, but in principle, what the theoreticians have predicted is that we would have a logarithmic correction to the classical exponent, to the, let's say, mean field exponent. And we have only few examples. In reality, I think TGS was examined. This one was examined, KDP, and probably 2 or 3 other ones, uniaxial ferroelectric, but the results are not very conclusive because if I remember also what I will tell you tomorrow is that the logarithmic correction is quite large. And so, okay, if it was a simple, let's say, correction, it would be okay, but here it's something which completely modifies. And also we have, as I remember, also incomplete result. In reality, the problem is that, let's say, measurement of critical exponent, and probably Professor Aharoni will tell me that because I left the subject a long time ago about the story of critical exponent, but at some moment people stopped to measure. There were other, let's say, interests in condensed matter physics, and all the measurement which I know are dating from the maximum end of the, let's say, 80s. And so it's already 30 years that things have been left. So it's like that. You have also passion sometimes.
Okay. Other questions?
May I ask a question?
Yes.
Sure, Adam, go ahead.
At the very beginning of your first lecture, you mentioned something called, I think it was a morphotropic transition.
Yes.
Could you say what that is again? Sorry.
Yes, the word morphotropic has been used in a bad way only for speaking about one material which has a morphotropic phase boundary. Okay, but morphotropic means simply, if you take the definition, that the content change, the concentration of one or two components are changing. So you have, let's say, stoichiometric phases, for example, VO2, V2O4, which are separated by a large biphasic region where you have non-stoichiometric composition. And of course, it's the domain of solid state chemists, let's say, mainly this morphotropic, it was. But in reality, it's a phase transition. And we have to, if you go to reconstructive transition, then you are tempted to go to morphotropic transformation because they represent an extreme case of difficulty, let's say. It's transition between two phases which have a completely different structure, can you relate this structure? I can tell you, the answer is yes, you can. With one of my colleagues in Germany, we wrote a paper on the morphotropic, let's say, a theory of morphotropic transformation, showing in the case of the vanadium oxide compound, because you need to take a concrete example if you want to show something real, you can explain all the phases as coming from a single parent phase. But of course, you need first to take two stoichiometric phase, find a common, then two other, and then you join all the results, and you find that all of them come from the same parent phase with a really very nice mechanism. So morphotropic transformation, which are transition between phases having a different composition, there is a theoretical, at least a symmetry can say something. But they are, of course, you don't even speak about first order because they are in different regions and you don't jump from one to another. These are, is it okay?
Yes, great, thank you.
So it's like a phase transition accompanied by a chemical reaction. Can you say it like this?
Yes, of course, you have, because to form V2O4, starting from VO2 and adding some vanadium and so on, you need to have something that will happen. But it's a very, I mean, we must not be frightened by difficulty. Let's say. I started being interested by the graphite diamond transition. I wanted to understand the mechanism. It took me a long time. I failed, but when I visited some colleagues in Russia, they had the solution. And so we began to work together, and we established even a book on the subject to show that you can describe reconstructive phase transition using the Landau concept. Of course, you have to extend the concept of order parameter, you have to extend almost everything. But the extension is very interesting mathematically. For example, okay, I don't want to enter because it's not at all the subject, and tomorrow I will not speak at all of that. But only, I mean, if you have time, let's say later, try to look on, let's say, reconstructive phase transition, and perhaps, because nobody, no theoretician, it's reconstructive transition was the chasse gardée, the private garden of metallurgists, of also, of course, mineralogists, and then of high pressure physicists. Then people from DFT who can measure whatever they want also try to use some DFT to predict some structure. But in reality, a real deep theoretical work has not been really done in this direction.
Pia, I also have a question. So, okay, you presented to us Landau theory, and you argued that to describe some features of phase diagram, you have to use maybe polynomials expanded to high degree and so on. So you should realize that that's not something that we have seen in textbook. So I want to ask some question. So I can believe that maybe if you're just talking about first phase diagram and first order phase transition, maybe you have to do something like that. But it I would find very surprising if these high degree polynomials, I don't know, you mentioned 12, 10, would be needed to describe some second order phase transitions. So can you say something about this?
Yes, I can give you, I recently found that, I don't know, a couple of well-known researchers show that you have to go to 8° to show that a phase that was found experimentally could have some stability. So I mean, of course.
But was the transition to that phase second order?
This I don't remember.
That's what I'm trying to say. So I would think that these phases for which stability you need high degree polynomials, then the transition to these phases would probably not be second order. But okay, that was my question. So
yes, we try to eliminate the problem as non-valid for second order transition. I partly disagree with you. It's true that all these low symmetry phases cannot appear below the parent phase across second order phase transition, but they can be joined by second order phase transition through intermediate phase. And I believe that you are interested by all second order transition, not only the first second order transition which appear below the parent phase. And we can have
I mean, the concept of parent phase is arbitrary. I mean, the moment you got to some phase, I can call now that phase a parent phase and so on.
No. This is not true.
Why not?
For structural, it's the phase which contain all the symmetry operation and which allow to construct the free energy. The parent phase, I mean, it's not some arbitrary choice. In reconstructive transition, you can say what you say, because the two phases have, for example, if you go some cubic to an hexagonal phase, which is the parent phase? This is not easy to say, but you can say something. But concerning this type of structural transition, the parent phase, of course, you can say it is always the liquid phase, but if you take a solid phase, the parent phase is the highest symmetry which appears generally below the melt, and you cannot say that it's some phase, any phase in the phase diagram. The highest symmetry appears at high temperature or at low pressure for transition under pressure. But the parent phase is the most symmetric phase in your phase diagram. You can, of course, think that you have a higher symmetry phase which did not appear in the phase diagram. If you cannot, I can give you an example. If you find more domains in the phase which appear in your phase diagram, which are not predicted using the parent phase that which appear first, then of course you can say perhaps there is a latent parent phase which is not here in the phase diagram, but that should be taken as the parent phase for the system. This I agree with this idea that you can introduce a latent phase if the phase that you have under your hand are not enough to explain all what you observe. But in general, the parent phase, let us not complicate a problem which is quite simple. It's the highest temperature phase in the phase diagram, and all the phases which are below on cooling, they are, if we deal with this type of structural phase, they are associated with subgroup of the group of this parent phase. Let us not imagine situations which have not been observed.
Yeah, but now my question was, so you got to this from the parent phase to some phase with a smaller symmetry.
Yeah.
And now from that phase of a smaller symmetry, I am studying a transition to yet another phase, which maybe has even smaller symmetry. So in order to describe that second transition within Landau theory, I don't need to know anything about the parent phase. I can now write my Landau Hamiltonian with respect to this second symmetry, and Landau theory is consistent, I think, under such passages.
I disagree. I can give you an example. I'm sorry to give my example in, let's say, this that was in fashion until recently, multiferroids. You know, it's the coupling between, you have magnetic phase transition. And you have a beautiful sequence of 2 second-order phase transition in most of the multiferroids. The first multiferroids, 2 second-order phase transition. The first one is purely magnetic. Okay, but you don't lose time reversal by you keep time reversal in the point group. And the second transition is again second order, but you lose the inversion center. Now, what you are saying is that you can deduce the second phase where you lose the inversion center only from the intermediate phase which appears first. It's not true, because in reality, what you discover when you do a clean Landau approach is that it is a coupling of the 2 order parameters. The one who gives the first transition and the one which gives the second one, when they couple, then they give, I mean, you need the coupling, and this coupling explains many things. Why, for example, at the beginning you have a Curie-Weiss magnetic susceptibility, but the second one is a very small, let's say, magnetic susceptibility, but still Curie-Weiss, I mean, the same shape. And also why the polarization, which is the coupling of 2 order parameters, the first and the second one. So you see, you have a coupling, but you have a sequence of 2 second order, and they are really second order phase transition. What is true in what you say is that if you want to describe the parent phase, you need, of course, always to take a phase above. The Landau theory gives you only the behavior of the symmetry which appear below parent phase. They don't give you the property of the parent phase. The parent phase is given. You have its symmetry, and okay, and you cannot say much more about
yeah, I think I understand, Pierre, what you said. Yeah, I think I agree that in some situations it's good to have parent.
So the only thing what I want to say, as I understood, you are interested by second order transition, but you.
Yeah, I understand. So it would be interesting to know how much of what all this complexity that you presented and high degree polynomials and whatnot, how much of this is necessary if we are just interested in second order transitions.
No, you see, I showed phase diagram which were, let's say, very seriously calculated, and where you have a sequence of second order phase. You can have, not always, that sequence of second order transition. And sequences, because there was an underlying idea, I remember precisely Louis Michel, he had the feeling that when you have a second order transition, it's always the first one. And then after it's necessarily first order. This is not true. You can have a sequence of second order phase transition. Only it's not so common, let's say, but what is common, what is not common, perhaps we need more time, more.
But when we go to the second order transition, where this in your Landau Hamiltonian, this high degree polynomials appear. I mean, you did the renormalization group theory. You know that in high degree polynomials, the renormalization group theory, they don't play a role. They are irrelevant. So we should replace them by some sort of quartic polynomials. Do you say that close to the second order transition, even though there are these complicated high degree polynomials, they will be somehow replaced by quartic polynomials in some way?
No, 6 degree is 6 degree. You cannot lower arbitrarily a degree because, let's say, yes.
Maybe close to the transition, somehow this polynomial gets simplified and it's approximately 4th degree plus some corrections, something like that.
I would like to say you yes for your pleasure, but I don't think it.
Maybe it's good. It would be good to have an example so
yes.
that you can work it out. It would be good to have. So you mentioned some things. You said, okay, it would be good so everyone should work out some irreducible representation of a space group. So
Only
if you can
two
provide
of
some
the-
example, which is like not the most trivial, but also not the most complicated, then
Yes. For example, you see and I know that Professor Aharoni will speak about that, about strontium titanate.
yeah.
Strontium titanate has exactly, it has a three-dimensional irreducible representation, but the other one, the one which gives only ferroelastic, a sequence of ferroelastic, 8 phase ferroelastics. And so you can see when you construct the two sets of 48 matrices of PM3 bar M, why in one case you have only polar phases, in the case of, let's say, barium titanate, and why in the case of strontium titanate. And of course, I can, it takes 1 hour. Give me any parent group, give me any K vector, and I show you the method to construct irreducible representation.
Okay. Okay, maybe we should then, if I don't know, are there any other questions? Because I was a bit more impolite. No.
Thank you.
Okay, I'm going to stop the recording then. Thanks a lot, Pierre.
Right.